All right, hi, I am Jason Gilman, and I'm the AI/ML applications lead at Element 84. And we're going to talk about applying large language models to geospatial search and analysis. So some quick plugs first. There's another Element 84 talk going on right now, but I think you've picked the right one to be in. And we've got a bunch of other talks. So I'm going to put a special emphasis on the embeddings one. That's going to be a great talk to go to after this one. There's going to be some really cool things that I'm not going to get to that I'll just be able to say my coworker Adil will be able to explain how those work. All right, so what are you going to learn today? We're going to learn how to combine geospatial and generative AI. I'm going to tell you how to think about LLMs because they have particular use cases that they're good for, and it's good that. I'm going to give you some great tips to be successful in all of these different things. And I'm going for breadth and depth in this talk in 30 minutes. And thank you to like the 8 people who filled out the poll out of 86 people who signed up to come here. You got to choose which of the topics I said I was going to talk about would actually fit in here because it all doesn't fit in 30 minutes. All right, so we're going to get moving. We're going to go quickly, but hopefully not too fast. How do we apply generative AI to geospatial problems? We've been thinking about that at Element 84, and you have users on one side who have important questions that we want to be able to answer, and you've got your data on the other side, right? We have documentation, text-based data, and APIs, databases, and stack catalogs and whatnot, and we want to be able to find a way to answer those questions. And at least for this talk, I'm going with the metaphor of a natural language geospatial computer. And I'll explain more about that and what's inside of the computer as we go. All right, so how should we think about LLMs? One thing you should know is that they can't do anything. And by do, I mean affect change in the world, talk to something else, talk to an API. If you're used to using ChatGPT, you know, like, well, wait, it can search the web and it can tell me different things that it knows about from other places. I can give it a link to a web page and it can summarize it for me. And that's because when you're talking to ChatGPT, it's not just a model. It's a whole system of stuff. There's a lot going on there beyond just the model itself. If you ask just an LLM, find me the location of all forest fires in California over the last 5 years, it can't do that. It's going to tell you it doesn't have access to the historical data. It doesn't have access to data right now. If you even ask it, what time is it? The LLM doesn't know. Like, they really are this sort of encased box where you pass in some data and you get data back out. And so we can think of them kind of like a CPU. I'm not the first person to make this comparison, and I read it online, link at the bottom, which is an interesting approach. And they talk about thinking about the prompt that you send the CPU LLM, that's kind of the RAM that you're sending to it, and then it outputs data at the end. They are bad CPUs as well. They are non-deterministic, right? You ask a question, you ask it again, you might not get the same answer. They're based on probabilities. They have been known to hallucinate, right? Make up things. You can ask a question and get an answer back, and maybe depending on the probability tree that it went down, the tokens that it was generating, it might go off in a direction where it's not actually producing a correct answer. They're energy hogs, and in terms of training them, they use a tremendous amount of energy, and then potentially during inference, you're using a lot of a lot of energy as well. And there's things we can do to reduce this. I'll go into a little bit of that in my talk, but they don't have to be. They're also a black box, right? If you ask an LLM a question and you ask it to do some math and give you just the number back, you don't know how did it get to that answer. And you can ask it, explain how you got to that answer, but it won't actually be how it did it. If you ask an LLM to explain how it's getting to an answer, that actually changes the quality of the answer that it's getting to as part of generating text that impacts what it's generating later. And because of this, people have a worry about trusting the answers that you get back from it. So why should we use LLMs then? And the most important reason is because of this connection to people, right? People have questions, important questions that they want answers to, and people communicate via language, via spoken and written language, and LLMs, for all their problems, have an amazing ability to understand and be able to pull out these details. LLMs are also generalizable, so they can answer questions, generate text, SQL, JSON, all sorts of different things that they've been trained on and summarize. Additionally, they're really good at autonomous decision-making. So if we have all of these particular places where we could answer data from, like documentation and APIs and whatnot, depending on what the user's asking, we need to go to different data sources. We need to go in different orders, and an LLM has sort of this emergent intelligence where it can figure out and answer these things for us based on descriptions that we give it. And so what we need to do is combine written code in the concept I'm calling a broker, which does everything that an LLM can't do. It receives natural language requests, and it decides when it should use the LLM to handle its portion, and then the broker can do everything that the LLM can't. It's deterministic. We can see inside of it. We can debug it. You have control over exactly what it does, and it can talk to other systems. And we have a good separation of duties here, where we can treat both of these things sort of as co-processors in a computer. And the LLM sort of becomes this natural language specific processor. So this is the inside of the geospatial computer. Like every computer, it's going to have a interface, and we're thinking about it as a user interface like in the web, where it incorporates chat and maps and diagrams and graphs and conventional or traditional user interface elements. There's a whole talk we could give on how you design UIs like this. One thing that I should note is that as a UI is communicating questions that a user's asking to the broker, it's going to pass along context. Like, what is the user looking at in the map? Where have they zoomed to? Have they selected anything? Any other inputs that they've put in? Who is this user? Like, what is the current conversation? All of that could pass this context to the broker to help answer questions. We need a place to store this data, so there's going to need to be a database for persistent state where we store information about the user and their preferences and ongoing conversations. On the back end of our computer, we have storage in the form of a vector database and a knowledge graph. And these index information about the particular data that we want to answer questions about. And I'll get into these more later. We're going to jump now into actually starting to do some geospatial stuff with LLMs. All right, so extracting data. When a user asks a question, like where are the current fire risks within 20 miles of Boulder, Colorado, we want to be able to understand what that is, right? To the system, like our Python code that we're writing, it's sort of an opaque string. And so we want it broken apart into a data structure. And so we want to be able to look at this and pull out the things like what the user is looking for, where the where in here is, they mean a map, and current and within 20 miles of Boulder, Colorado gives us an idea of temporal and spatial part of it, and fire risks gives us something else. And so LLMs are really good at this. This is like one of the major things that you'd be able to use in order to answer questions. So we'll do an example here. We want to build a system that's going to be taking JSON like this, where we have a city and then some particular data point that we want to load up. And the user asks a question like, what's the average rainfall in Seattle? We can use Pydantic as a tool to extract out that data. And so I'll show you some snippets of code here. We first define our Pydantic model, and basically what we're doing is we're just making a Python class with some fields. These are the fields that we want populated in our JSON. The documentation that we put in our class, including descriptions on the individual fields like city and state and feature of interest, all gets put in the JSON schema. And that helps the LLM know what's possible in the JSON schema and know what each of these fields are for. The literal here, where we're saying the type of this gets put in the JSON schema as well to know that it can be one of these two choices. So that's pretty easy. And then we write a prompt. We tell the LLM what its job is. We say use this schema, and Pydantic generates the JSON schema for us. And then we put in the user request. We invoke our LLM, and we get back the response. It's just JSON at that point, and then we can parse it. So pretty easy way here to take natural language, use an LLM, and get it back in a data format that we're saying. You'll notice in my made-up method here, which is going to be different depending on what model you're using, I put JSON mode equals true. If you ask an LLM a question like, produce some JSON, they tend to be really wordy and say like, okay, I'll go ahead and do that for you. Here's the JSON you asked for. Every single token that LLM is outputting takes time, and we want it to be easy to parse, but we also want performance systems. A lot of these systems that we're building are going to involve multiple calls to an LLM, and everything that we can do to just shrink down the prompt that we're sending to the LLM, but also have it come back as terse as possible, improves performance. There's a little bit of a trade-off there in that actually getting the LLM to be a bit more wordy can actually improve the answers, but you have to sort of depend on the problem that you're facing. Turning on JSON mode is really dependent on the LLM, so I recommend reading the guides and read the whole guide on the LLMs. They're really useful. All right, so natural language geocoding is an example of a feature that we built based on the idea of data extraction. With natural language geocoding, it's something that Element 84 invented, where we can take a natural language description of a spatial area on the Earth. And this is like really important. Every question that's going to be geospatial related is going to have some form of this, whether it's just a city name or something more complicated than that. And the way that we do it is we think of a spatial description as sort of pseudocode. When a user says within 10 kilometers of the coast of the Iberian Peninsula, they're sort of saying, I want you to do a place lookup and give me the coast of that and then add a buffer to it. And then we have a directed graph here, which is easier to process in a system. We can, going from the root of our tree, or not the root, I guess the leaf here, do a place lookup in OpenStreetMap. To get a polygon, we then do a spatial operation to compute the coastline, and then add a buffer to it. And so that's the way natural language geocoding works. We take a prompt where we have a JSON schema that describes all these different spatial operations that we can do, place lookups and things like that, and the LLM decides how is it going to represent that user's spatial area that they're describing within this JSON schema. And then once we have our JSON, we parse it, and then we can just operate across that tree and produce that polygon. All right, I told you we're going through this stuff quickly. We're going to cover a lot of stuff here. Generating SQL, right? You have data in databases, and SQL is great for looking at that data, for being able to like search through it and do things like aggregations, but we don't want to expose that to our users. Usually that's not the way that they want to express things. So they want to use natural language to do it, and LLMs are really good at this. This is a kind of a standard feature at this point where you can do it, and here's what a prompt looks like that will be able to generate SQL. We tell the LLM, basically give it some context, here's your job. We then give it a description of all the tables that are available. And you can do multiple tables here. We just have one particular table here with some weather data. And then we describe the different columns that are available. We make sure that they're really detailed descriptions and the types, and we indicate like joins and things like that to other tables. And then the LLM is able to understand it at that point and generate SQL. You're noticing at the bottom here that I have a sentence, generate a valid SQL query only without any accompanying text. This last part here is sort of like SQL mode. It's basically I'm telling the LLM, don't give me all the stuff about how you're doing a good job making SQL, just give me the SQL back. This is faster, easier to parse. And there's one other thing I want to point out here. If you write the word valid in there, and you put it in uppercase, both of those things make the LLM do a better job and produce better SQL more often. So we should just think about that for a moment. It's it's kind of scary. We want to build reliable systems, but this is how it goes. It reminds me of when a developer says, like, they're looking at a timing bug and they say, don't worry, I fixed it. I added a sleep. And you're thinking, like, no, you didn't fix it. There's something else that's still there. And it's like the same thing, right? Like your developer / prompt engineer says, don't worry, I fixed the bug. I told it, like, I'm really serious this time, make correct SQL. And it does do that. So this is a pet peeve with LLMs, and it's part of the nature of them. They are non-deterministic, and it's possible that they will generate something, and we can set the temperature really low, which changes how often it's going to choose, like, the most likely token next. But you have to be prepared for the LLM to make a mistake, right? So you build that into your systems. You do a lot of testing with different things, and if the SQL is invalid, you should be handling that. Potentially ask the LLM, can you fix this? And a lot of times they can. They'll say, oh, I'm sorry, here's the better SQL that you should use. Retrieval augmented generation. So you've got data that's not just data in databases. You've got documents and websites and metadata and tutorials and videos and podcasts and everything, right? So users are going to ask questions that might come from this data, right? There's so much information there, and so we have to be able to answer those questions. You've probably heard of retrieval augmented generation before. It's already been mentioned probably a few times. But the basic idea, if you're not familiar with it, is you're going to take documents, chunk them up into semantic little individual bits, and we index them into a vector database. Vector database makes it easy to search for semantically related pieces of information, and go to the talk later on vector embeddings, because I don't have time to explain it now. When a user asks a question, right, they're asking about a specific topic, we go to the vector database and we say, here's the topic as a vector embedding, find me the similar chunks of data. And we take those chunks and we go to the LLM and say, okay, can you answer this now with this information? And so we're grounding the LLM in this context, and that improves its ability to answer questions on stuff that it already knows. It has less hallucinations. It can cite the sources. It can put, like, here's the page number that came from. But it also gives you the opportunity to give information to the LLM that it wasn't trained on. There's a couple different storage options for RAG data. I mean, you could just put it in a regular database too and just do, like, a text-based search on it. Vector databases do a pretty good job of searching for similar chunks. I think knowledge graphs are maybe the future of where RAG is going, and I'm thinking a lot about that. When you take a chunk out of a document, you're really taking something out of context, and anything in there where it's saying, and the thing that I just explained to you is good for these reasons, what were they referring to, right? If it uses the word it, like, what did it refer to if it didn't happen to be in that chunk? And so with knowledge graphs, you're doing more work in the front end to pull out facts that are standalone. They are true in and of themselves, and LLMs can go and, just checking my time here, LLMs can search that, generating a Sparkle query, and be able to find the right data, and then you can put this information in the message to an LLM, into the prompt, and it's really grounding it in, like, exact, clear, unambiguous facts. Vector databases are a lot easier, and they're a good way to get started, and that's most of my experience so far has been on using vector databases. My tip here is, like, spend most of your time on the chunking, right? It's getting those chunks clean with just the information that makes sense to be together is the most important part. There's tons of strategies, but I'm just going to go straight to what did I find most effective. The thing to do first is to clean the text. If you're pulling things out of a PDF, right, you're going to be pulling a bunch of cruft along with it. Like, every time that it has, like, a header at the top that says copyright blah 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 is going to be in the middle of everything that you're doing. You have to remove all that stuff, and then after you do that, then you're going to start breaking them up. And so you're aiming for a chunk size. I found 1,500 characters was about the right size to be most effective, and this is actually a bit larger than what people recommend. So I think you should test different sizes. You need to split up things to get within this size limit. treat documents as trees. This is, I found, most effective because the document's already split up into things that are semantically kind of separated. Use the document's natural structure, which means you need to understand headings and things like that and build like parsers. And so you end up spending a lot of time here, but it ends up being worth it in terms of the answers that you get on the other end can be really good. The sections themselves, if they're under 1,500 characters, you're good. Index that. If it's bigger, then you need to start splitting it down, first by paragraphs and then by sentences. So you're just sort of treating the nature of the document into unique things that can stand on their own. You also need to pick an embedding model, and this is the thing that's going to generate vector embeddings that lets you put it into the database. I found AWS Titan Text Embedding version 2 to be really good and also handle this size. Some of them you'll try to do 1,500 and it'll tell you like that's too big. Agents is where we're rounding things out. So now that we know how to do all those different things with RAG and with extracting data, agents are the things that let us connect all that stuff together. So the way that an agent works is you present the LLM with, here's a user question, and here's a bunch of different stuff that I can go do. What should I actually do next to answer this user's question? You then go do that, the LLM tells you, and you come back to the LLM and say, okay, I did that, here's what I found, what should I do now? And you do this iterative cycle where you're going and doing something and coming back to the LLM to get answers. And I'll show you here, we'll step through it. So here's what a prompt might look like, and your tools here will have good descriptions, and there'll be things like searching a catalog, we're doing aggregations, or downloading a file, or even going back to the user. Sometimes you need to clarify stuff or say like, I couldn't find this information, did you mean something like this? The LLM will first choose what it wants to do. If we go back to the example that I had on the screen, where are the current cases of Lyme disease within 20 miles of Boulder, Colorado? The LLM might first say like, let's do natural language geocoding. We want to get like that precise polygon before we go forward. So you go and do that, and you come back and you tell the LLM, okay, LLMs don't have memory, by the way. They can't remember anything. They're stateless. So we have to tell it what we were doing. Like we were answering a user's question. You told us to do natural language geocoding. I did it. Here's what I found. What should I do now? And so then the LLM is going to tell you then, okay, let's do a catalog search or whatever else it is. And you can then go do that search. The LLM might even give you should be able to give you the information needed to invoke that tool. And then you can go back. And this is just an iterative process until you get to the end where you now have enough information. The user says, let's display this to the user and let's use a map. So some tips on agents. Keep it simple, right? So this can get complicated quickly. So I'd say start at a small number of tools and increase from there. Tools should be one job only, right? In terms to make it easy for the LLM to understand what the tools do, you want to have extremely detailed descriptions and keep them cohesive, as in like it's not a pair of scissors and a calculator, it's just calculator or scissors. And then this is going to take a while, right? Every time you invoke that LLM, there's going to be some number of seconds before you get a response back, and then you go do some other stuff. So you need to keep the user informed. And so you need to build as part of the system a way for the broker to inform the user through the UI, here's what I'm doing now. And at the end, we don't want to just give the user an answer. They want to know how you got there, right? A lot of these are scientific reasons that they want these, and science doesn't work without being open and knowing how it got there. So you want to show the user what data did I use? How did I do that? What algorithm did I apply? And then the user has the option to say at that point, oh, that wasn't what I meant. So actually I mean this other thing. And then you can kick off another one of these to get to the answer. My last tip here, focus on the user, right? A lot of AI, ML stuff kind of looks at what's cool and shiny, and I mean, I do that too, but we should always be looking at what are we building this for, and who are we trying to help? So that's it. Thanks.